All right, good morning now. Well, I feel we've now come to a very nice place in the course. You've been working extremely hard. We've just gone through what I said I felt was really the intellectual pinnacle of sophomore organic chemistry. We've been through a very rich collection of carbonyl chemistry. You've experienced it with the enolate and enol chemistry on this quiz, and in this week's discussion, you'll be getting reinforced some of the things we talked about in class last week with all of these wonderful reactions, the aldol reaction, the Claisen reaction, the Michael reaction, the Robinson annulation reaction, all this ability to recognize interrelationships in a molecule, beta-hydroxycarbonyl compounds, alpha-beta unsaturated carbonyl compounds, 1,3-dicarbonyl compounds, 1,5-dicarbonyl compounds, and cyclohexenones. And so at this point, at least as far as the lecture part of the course, that's behind us, and now you're going to be working on that and reinforcing these concepts through the discussion section and the homework problems and our last quiz. So we come into the last few chapters of the class, and I think this is a fun point in the course. We've done a lot of hard work. We're still going to have a lot of nice ideas. This week, we're going to be talking about the chemistry of amines. And in some ways, in a course like this, this is a neither here nor there chapter of the class, because you've gotten a big richness of the chemistry of amines already. You've learned about their reactions to make amides. You've learned about their chemistry as acids and as bases. You've seen some generation of amines when you studied aromatic chemistry and electrophilic aromatic substitution. So in a way, this week's chemistry is a bit of a refrain. We'll see a few new cool reactions, some cool syntheses, a few neat mechanisms. The next week, we're going to come into the chemistry of carbohydrates. And carbohydrates are going to bring in some carbonyl chemistry. We'll see chemistry of acetals and their formation and their breakdown. We'll see some chemistry of enol, keto, tautomerization, and some acid-catalyzed reactions. We'll come way back to ideas of stereochemistry. We got a little bit of this as we talked about some of our aldol chemistry, and we reviewed some ideas of enantiomers and diastereomers, and you'll get more of that. I'll try to bring in some of the molecular modeling that we did. If things work out right, maybe I'll ask you to bring your computers into class. I'll think about that next week, but be prepared to maybe bring your laptops in next week. And then the final week of class looks like it's going to be a big thing because we've got a couple of chapters. And I want to pick out a few highlights. I guess there's chapter, I think if I remember the numbers, there's chapter 28, and I may have the numbers wrong. But there's a chapter on amino acids, peptides, and proteins. And some of this is going to be redundant with your biochemistry chapters. I want to focus on one aspect of that, which is another real intellectual pinnacle of organic chemistry, and that is the solid phase synthesis of peptides. And that'll bring in some nice reactions. You'll see amide bond formation. You'll see some concepts of aromaticity and stability of anions. And you'll see a really profound idea of being able to build up molecules repetitively, step after step, biologically important molecules, molecules that are all sorts of things, hormones that lead to uterine contractions in pregnancy and birth and so forth. And this was one of the intellectual triumphs. And if everything works out in our timing, and I'll give you a selection from that chapter, from the amino acids chapter, selection to work on. And if everything works out right in our very last class, one of my big laments in organic chemistry is that a lot of the really modern concepts, I mean, some of the chemistry you're going to see goes back more than 100 years. We've talked about some of this chemistry. in some of the reactions we've discussed, like the aldol reaction and the Claisen reaction. But if everything goes right, in the last lecture, we'll get just a taste of organometallic chemistry. Not Grignard. I mean, we've already done Grignard chemistry, but chemistry in which metals can act as templates to form carbon-carbon bonds. So we'll see how things go. So today I want to start by talking about amines and talking about their properties and their syntheses. And amines are really cool molecules and really important biologically. They're present in so many biologically active natural products. Many of these are called alkaloids and are produced by plants. And I want to draw out two of these molecules, and I want you to draw along with me. They look really hairy, so I'm going to draw at least the first one. I'll draw slowly. It looks really, really hairy. So we're going to start by drawing a benzene ring, like so. And we're going to connect that to a cyclohexane ring. We'll make it a cyclohexene ring. For those of you who, well, for everyone here, you'll know my handwriting's no great shakes, and yet a few simple tricks like being able to draw a hexagon or being able to draw a zigzag line really help. We're going to connect these two rings together by way of an ether linkage from the benzene to the cyclohexene ring, and I'll show some stereochemistry over here. We'll put on a couple of hydroxy groups, one on the benzene ring, and of course there's no stereochemistry on that hydroxy group. And then we'll have another hydroxy group going down. In other words, in a stereochemistry going down. We'll draw in one more six-membered ring here. So far everything's pretty easy to visualize. Now we've got some overlapping bonds, so I'm going to put a bond, a wedge, an arrow, a line coming out of the blackboard to a nitrogen here. And again, if you're good at drawing hexagons, you can do a lot of things and then fake the rest. So we'll have another bond off of the nitrogen. Going to show a bond coming out over here, like so. We'll connect that over to the bond to the nitrogen, so we're crossing. If you want to get fancy, and people who are really good can do this beforehand if they just plan their drawings. I'm not really good at drawing. You'll put a little break in there to help indicate that we're going above. So that doesn't mean a broken bond. It's sort of a way of drawing perspective. So you've got that. I'll show you some stereochemistry over here, a hydrogen, and we'll finish our molecule off by putting a methyl group on the nitrogen. Does anyone know what this molecule is? Morphine. Who said that? Good. Who? Morphine. Good for you. How'd you know? What's that? Ah, did they? Okay, so I didn't see morphine in the chapter. I saw, okay, so great, great. And this is a really important molecule in organic chemistry. And when I teach my graduate level spectroscopy course, I tell students that it took chemists 50 years to determine the structure of morphine. And now this is something that our graduate students can do in the course of an afternoon. I didn't see morphine, but I saw at least one related compound in the chapter. So morphine is part of a family of what are called alkaloids. Alkaloids are nitrogen-containing compounds produced by plants. Morphine in particular is an opioid. It's produced by the opium poppy. Incredibly important in pain relief. After you know, all of decades upon decades of pharmaceutical research, when you have really bad pain, terminal cancer pain, and all sorts of horrible things, morphine is still the drug that is given. And of course, as an opioid, it's an addictive drug, but you know, at some point, if you have terminal cancer, it doesn't matter. Many of the synthetic drugs that also work on pain bind to the same receptor in the brain, and it's really hard to separate pain relief from the ability to get addicted. The one I saw in the chapter, I've never taken morphine myself as a drug or in any other context. The one that I've seen in the chapter has a methoxy group over here. If you have, instead of a hydroxy group, you have a methoxy group. That's another opioid. It's codeine. It's great cough medicine. I've taken that one. It's potentially abusable, potentially addictive. Morphine and opium, of course, are widely sought after. I mean, we've got tremendous trouble with drug trade from Afghanistan and so forth, where poppies grow. But what really makes morphine, unfortunately, valuable as a street drug and highly sought is its diacetylation. In other words, if you take morphine and you treat it with acetic anhydride, you get the diacetate over here, an acetoxy group. Anyone know what that drug is? Heroin. Very easy to make heroin. So as I said, morphine is an amine, and it's specifically a tertiary amine. It's a nitrogen with 3 groups on it. I want to draw one other alkaloid. Your textbook really goes to town talking about everything from neurotransmitters like dopamine and serotonin to nicotine, another addictive, highly addictive compound, to all sorts of other molecules, spermine and spermidine. So I'll draw one other molecule. It's based on a bicycloheptane skeleton. So I'll draw out that skeleton. I'll show you a little trick of mine as well. So we know how to draw a cyclohexane ring. And I'm going to show you that everything else you can fake if you can draw one thing. So the one other bicyclic structure that I like to be able to draw is norbornane. And if I can draw this, it's a cyclohexane in a boat with a bridge. If I can draw that, I can sort of fake everything else, because the structure that I'm drawing now is basically norbornane with 1 extra methylene over here, and so you can sort of fake it. And we have, in the bridge position, a nitrogen. It's a methylated tertiary amine group, just like we have in morphine. I don't think this one's in your textbook. We'll have a methyl ester group over at this position. We'll have a benzoyl group over at this position. Anyone know what this molecule is? Cocaine. I have had that one medicinally. When I was in college, I used to get terrible nosebleeds, and so to treat it, apparently the treatment involved some silver nitrate up your nose, but before that it was preceded by some cocaine up your nose. That was another one I used in my graduate level spec class. One of my colleagues is authorized to have a bottle of cocaine for research purposes, so I was very happily walking around with a 1-gram bottle of cocaine that was to become the final exam for our graduate students. All right, so all of these compounds, and you can see how, and one of the cool things about this is, by this point in the course, you should be good enough with functional groups. So when I go ahead and show you a big hairy molecule like morphine, and I say, yeah, we treat it with acetic anhydride, even though maybe your textbook examples might have included treating isopropanol with acetic anhydride, to get isopropyl acetate, you can understand that these same principles of reactivity apply. You've got a basic amino group in there. The amino group is going to behave as a base. You can extract alkaloids into aqueous acid solution by protonating them. And then you can go ahead and remove various impurities and then go and treat with base and extract back into organic solvent. So you can recognize functional groups. We have an ester group over here. Okay, so the group there is a tertiary amine. I suppose the group is a tertiary amino group, but I'm going to write tertiary amine and just write a generic structure R3N. And I'm not going to be so fussy as to go R1, R2, R3N, but of course you can have 3 different groups. We've used tertiary amines as reagents. You've used triethylamine as a base. Tertiary amine, of course, has 3 different carbon atoms attached to the nitrogen atom and a lone pair as well on the nitrogen. A secondary amine, again, I'm not going to be so fussy as to say R prime or R1, R2, but you have 2 alkyl groups, 2 R groups on the nitrogen, 2 carbon-containing groups. You've already encountered, we've used certainly again and again in our enolate chemistry, we've used this amine, we've used diisopropylamine. This secondary amine. Say primary amine. By the way, you'll see people write 1-0 for primary, 2-0 for secondary, 3-0 for tertiary. That's fine too. I don't know. For a primary amine, of course, we're talking RNH2 here. So I'll give us an example of methylamine, CH3NH2. Now, of course, one thing to keep in mind is there's a fundamental difference between talking about amines and talking about alcohols. When we use the notation primary, secondary, tertiary for alcohols, of course, we always have an OH, right? When you go ahead and have 2 R groups on an oxygen, that's an ether. It's a different class of compounds. But with alcohols, you'd say, okay, ethanol is a primary alcohol. Isopropanol is a secondary alcohol. Tert-butanol is a tertiary alcohol. So that's one thing that's different. All right, I want to maybe show us a couple of aryl amines. So these examples here are all alkyl amines. And there's some real differences in reactivity and even differences in the structure and bonding of aromatic amines and aliphatic amines. So I'll just show you a couple of aryl amines. So because the chemistry of amines is so old, so many of these compounds have common names that are used in preference to maybe a more systematic name. In fact, the common names have really gotten wrapped into the systematic names. So you wouldn't call that compound, no chemist would call that compound phenylamine or aminobenzene. They'd call it aniline. I guess somebody could call it aminobenzene. Certainly, if it's a substituent, you'd call it that. I'll show you that in a second. But I'll just give you one other idea for substitution. I don't think we're going to be as systematic maybe in our discussion of nomenclature as we've been with some of the other compounds, in part because amines people differ so much from systematic nomenclature and how they refer to them. So if we're going to refer to substituents on the nitrogen, we'll just put the capital letter N. If you're typesetting it, you'd set it in italic. So this compound has two methyl groups on nitrogen. So this would be NN-dimethyl-aniline. And maybe I'll give you one more example. So if you have, remember I talked about substituents and I said, okay, if you have like a carboxylic acid, in general, things are substituents. So for example, if you have a hydroxy group and a carboxylic acid and a long chain alkyl group, you'd call it a hydroxy acid, a beta hydroxy acid, or you'd say 3-hydroxypropanoic acid. Similarly, in terms of ranking and in terms of priority, the amino group is pretty far down the totem pole. So if you have a ketone or you have an aldehyde or you have an acid in the molecule or a nitril, you're going to be naming it as an amino substituted molecule. So this molecule here, we don't name as an aniline, we'd call this p-aminobenzoic acid. So one of the things that's really defining about amines, as a matter of fact, is probably the first or second word that I would think about when I think about amines is they're basic. And we probably also think of them as being nucleophilic. We've already seen lots of their chemistry as bases, and it's a good chance to review and also to straighten some concepts in our mind. So we always think of basicity, we think of the pKa of the conjugate acid as a measure of basicity. So the pKa of the conjugate acid of an alkylamine, something like triethylamine or diisopropylamine or methylamine, the pKa of the conjugate acid, I'll just write it in generic form. And so like this, the pKa is on the order of 10 to 11. There are a few numbers you should keep in your head. That's one. You can keep 10, you can keep 11, you can keep both. Doesn't much matter. Now, what a lot of students find confusing, and I hope by this point you don't, but it's always good to have a reminder to get things straight in your head, is that if you have ammonia or you have a primary or secondary amine, all of these compounds are amphoteric. And it's very important to keep this straight in our head. So when we talk about diisopropylamine and we talk about making LDA, we're thinking about a completely different equilibrium. So we know diisopropylamine, when we think about making LDA, we say, oh, the pKa is about 40. And of course, what we're doing, and I hope by this point that you're on top of this, is we're thinking about two different equilibria. One in which the amine is acting as an acid. So when you take diisopropylamine and say butyllithium, we have an equilibrium that lies so far to the right that for all intents and purposes, I barely think of it as an equilibrium, where we get diisopropylamine and butane. And here what we're saying is an acid, pKa 40, reacts with a very strong base to give a slightly less strong base, and a conjugate acid of butyllithium is butane, pKa about 50. Now, conversely, by the time you're going to do an aqueous workup on an LDA reaction, maybe you're using some aqueous acid like aqueous HCl, which I'll write as H3O plus because HCl is such a strong acid that it dissociates fully in water. You're going ahead and you're treating your diisopropylamine with H3O plus, pKa 17, negative 1.7, and now you're protonating this. So now, again, you have this equilibrium that lies so far to the right that I'm not even bothering to write it as an equilibrium, where now we're talking about, say, I'll give you an exact number. It happens to be 11 in this case, but again, 10 or 11 doesn't matter. And so that equilibrium lies way, way, way to the right. Now, one thing that's important to keep in mind in avoiding confusion is there's a huge difference between amines and amides. In amines, you have a nitrogen that's pyramidal. So this is an amine. It has a lone pair. If it's an alkylamine, it has a lone pair that's in an sp3 orbital. And for an alkylamine, it's not participating, the electrons are not participating in any significant resonance, and so that lone pair is available to protonate. Now, where a lot of students get confused the first time around is thinking in comparison to amides. And so I'll take, say, a generic amide, but of course it could be, in this case, dimethylacetamide. Now, the huge difference is, yes, you have a lone pair on that nitrogen, but that nitrogen is tied up by resonance, so it's not available. The lone pair is not available. If I had to characterize amides, I'd say simply not basic. It's not exactly true. They're basic, but very weakly basic. pKa sort of into the negative range, -1 for the conjugate acid. But they're not basic on nitrogen. It's the lone pairs on oxygen that actually protonate. That lone pair is tied up by resonance. And in fact, because you have a good degree of double bond character, for all intents and purposes, your lone pair really is more like sp2 hybridized, and your nitrogen is almost planar. I'll say little tilde, approximately planar. Just think of it as planar, and think of it as approximately sp2 hybridized. So I want to make a comparison between amines like diisopropylamine and triethylamine and methylamine and ammonia, of course. I mean, it's not an amine, but it's basically the parent of the same family, much as water is the parent to alcohol. And amines that have aromatic groups in them. So when I drew aniline, we also have a situation that in some ways is like our amide. You've got a nitrogen with a lone pair, but that lone pair is participating in resonance. The lone pair is donating into the aromatic ring. When you learned about electrophilic aromatic substitution, you learned that amino groups were ortho-para directors, that they were pushing electron density to the ortho and para positions of an aromatic ring, and then in turn able to stabilize a positive charge that formed during the electrophilic aromatic substitution reaction. So the lone pair is tied up by resonance. And it's sort of halfway between the degree to which it's tied up by resonance in an amide and the degree to which it's available in a simple aliphatic amine, a simple alkylamine. The pKa of the conjugate acid, so the pKa, so this is an arylamine. Aryl is just a fancy word for aromatic. And the pKa of, if you want to write it as ArNH3 plus, the conjugate acid of a generic arylamine, could be aniline, vary a little bit by substituents there. We're talking about 5. Whoops, not 50, 5. So in other words, not as non-basic as an amide, but not nearly as basic as an alkylamine. There are other nitrogen-containing organic compounds. There are all sorts of nitrogen-containing heterocycles, and some of them you should already know from discussion of aromaticity and structure and bonding. So for example, pyridine is the nitrogen analog, and I'll draw the lone pair here just to be very explicit. So this is pyridine. We've been using it as a reagent in some acylation reactions. Pyridine is the nitrogen analog of benzene. The nitrogen is participating in the aromatic ring system, and instead of having a CH group, it has a lone pair of electrons. The lone pair of electrons is sp2 hybridized. And remember, when you use more S character, you hold your electrons closer to the nucleus. That makes them more stable, less willing to share. So when you use more S character, your lone pair is less available to bond to a proton. That lone pair is less basic and less nucleophilic than a regular amine. So the pKa of pyridinium, the conjugate acid of pyridine, the pyridinium ion, is also about pKa of 5. I want to give you one other nitrogen-containing heterocycle, and it's one that you've probably seen before in your discussion of aromaticity. And this nitrogen-containing heterocycle is pyrrole. Now, pyrrole's another one I think that beginning students often find confusing, because you look at that, you say, oh, there's a lone pair of electrons on the nitrogen. It looks like it ought to be basic. And that lone pair of electrons ends up being part of the aromatic pi system. As a result, if you protonate it, you're going to give up a ton of resonance energy. That lone pair, just like the lone pair in amides, is for all intents and purposes not basic. Pyrrole can protonate, but when it protonates, it actually ends up protonating on carbon, not on nitrogen. So thoughts or questions at this point? Yes? Why can they, if they're all,
Like not very, it's not like,
so, okay, when we're talking about basicity, this is what I was talking about with the concept of amphoteric. When you're thinking about how basic something is, you have to throw a switch in your mind and say, that means I need to think about the conjugate acid. When you're talking about how acidic something is, so we're not discussing the acidity of Perol, then you're thinking about, okay, what are we doing to give up a proton and form the conjugate base? So remember, in your mind's eye, when we're thinking about the basicity of Perol on nitrogen, you're thinking about this species here with 2 protons, and you're saying, oh my goodness, I've had to give up all of that resonance energy, all of that aromaticity. That's terrible. That doesn't form. Perol doesn't have quite as much resonance energy as benzene, so you don't have, it's not quite as bad to protonate on the ring, and it's very reactive in electrophilic aromatic substitution. Now, okay, so as I said, to me, basicity really characterizes amines. The other thing, if I had to think about amines and sort of say, what do I think about amines? I'd say, to some extent, I think of them like alcohols, but less so in everything except basicity. And I'll show you what I mean in a series of discussions of properties in spectroscopy. So amines are kind of like alcohols, but less so. They're less polar than alcohols. Their dipole-dipole interactions are weaker. Their hydrogen bonding is weaker. So I'll say less polar than alcohols and less hydrogen bonding than alcohols. There are a few compounds it's kind of worth having in your head as a reference point. Methanol or ethanol are sort of good ones. You've probably worked with them in laboratory. You should know that methanol is a liquid. If you don't know the exact boiling point, you at least would know it's a volatile liquid. It boils lower than water. It happens to have a boiling point of 65. It's toxic. It's a lower boiling point than ethanol, but not that much lower. And unlike ethanol, it causes blindness, permanent blindness, not being blind drunk. So if I compare, say, methylamine, which you'd say, okay, it's about the same weight. It should have about the same, it's about the same size. It should have about the same van der Waals interactions. And so then differences are going to be in hydrogen bonding and dipole-dipole interactions. So methylamine, by contrast, is a gas. In other words, the molecules don't have enough interaction with each other to cohere into a liquid at room temperature. It's a gas until you cool it to -6 degrees at atmospheric pressure. Of course, if you have it at higher pressure, it's a liquid. Now, by contrast, again, to simple compounds, if you look at something about the same size, if you look at ethane, again, it's just two heavy atoms, 2 second-row atoms, and it's about the same size and the same weight. But you don't have dipole interactions. You'll have van der Waals interactions. You don't have hydrogen bonding. And ethane, of course, is a gas. Its boiling point is -88 degrees. So by the time you're down to a molecule of that size, you really have to go cold. So you look at this and you'd say, well, okay, methylamine is like halfway between methanol and ethane in terms of its interactions. It doesn't hydrogen bond as much. It doesn't participate in as many dipole-dipole interactions or as strong dipole-dipole interactions. And not surprisingly, that tracks with electronegativity, because electronegativity is basically a statement of the property of elements. And so nitrogen is less electronegative than oxygen. Nitrogen, the electronegativity is 3.0. And oxygen, the electronegativity is 3.4. In other words, the nitrogen pulls the electrons away from the hydrogen less, so they hydrogen bond less. You've got smaller dipoles in the molecule, and so for both reasons, that shows. And you can see this, so if you want to now separate out the hydrogen bonding component from the dipole-dipole component, I'll give you another comparison. So we'll look at trimethylamine, CH3 nitrogen. So that's a gas. Its boiling point, though, is just above freezing of water. Its boiling point is 3 degrees. And if we compare it to something comparable in size to isobutane, now we have a lower boiling point, although not that much lower. So CH3CCH is isobutane, virtually the same size and shape as trimethylamine. And the boiling point, it's also a gas. The boiling point is now -12 degrees. So you can look at that and say, yeah, okay, we've got dipole-dipole interactions in trimethylamine, and those raise the boiling point a little bit over isobutane that just has van der Waals interactions. But it's not a huge difference. All right, in so many ways, amines are lesser versions of alcohols. And it's probably in terms of what you see in the spec part of the course you get for IR, you're not going to see it, but when we actually look at real IR spectra, you see it. So in the IR spectrum, you have an NH stretch. And the NH stretch is essentially at the same place as alcohols. It's that region above 3,000, that region kind of around 3,300 to 3,500. So the NH stretch, I'll say it's like the OH stretch. In other words, you'll typically see, from your textbook, you can use 33. In my graduate course, I give more detail, but you can use 3,300 to 3,500 wave numbers. But when you look at an actual spectrum, what you see is the band's a lot weaker. Now, you're not going to see this, but maybe you will if there's some spectra in the homework. But what I mean is an alcohol really stands out. It really yells at you. An amine kind of whispers at you. You can look with a small amine and you go ahead and you say, oh yeah, I can see it. But by the time you get to a big compound with an amino group in it, it's very, very weak. If you have a primary amine, you'll actually see two bands that correspond to an asymmetric and a symmetric stretch. The other thing, and your textbook doesn't mention this, when I read an IR spectrum, I generally look at the region from about 1600 on up. Right at the very bottom of that region, there's an NH bend, and so it's right at about 1600. And it's just below it. The thing that I'll mention to you, since you may see it in your lab course, or maybe you'll see it in one of your homework courses, homework problems, it's just below where the carbonyl group occurs. So the carbonyl group, we said normally about 1700, but then we said for amides it can be about 1650 or 1660 or so. And this is just on the lower edge of that. So when you're reading a spectrum, you want to make sure you don't mix it up. All right, NMR spectra, again, this idea of kind of like an alcohol, but less so, comes up, or at least it's how I organize it in my own thinking. I'll show you what I mean. To me, when I'm thinking about an alcohol, I'm normally thinking about the hydrogens on the carbon next to the oxygen. And so I'm thinking, all right, that's sort of 3 to 4 ppm. That'd be kind of a range if you want to keep one number in your mind. I can give you a more detailed number. But when I'm thinking about an amine, and again, I'll just sort of write a generic structure, that nitrogen's less electronegative. It's pulling electron density away from that hydrogen less, and as a result, it's not shifting it as far downfield. So generally, the hydrogens alpha to an oxygen in an alcohol are going to be kind of in the 3.5 ppm range. In an amine, it's going to be in the sort of 2 to 3 range. Your textbook gives 2.3 to 3, which I think is a good sort of general assessment, but remember, those are always loose. In other words, dimethylamine is 2.3 ppm. By the time you go to a more sterically congested group or a more substituted group like diisopropylamine, you're more toward 3 ppm. The NH, so when we talked about alcohols, or when you talked about alcohols in spec, you said they're all over the map due to hydrogen bonding. And it's kind of the same thing about the NH group. Your textbook gives 0.5 to 5 ppm. And that's a good general start, unless you're an arylamine like an aniline, in which case it's going to be a little further down. But the NH is often very broad and hard to see. And so for those of you who go beyond the textbook course, I'll say often broad and hard to see. And by that I mean you take an NMR spectrum and you may be looking for the NH and say, oh, this can't be an amine, I don't see an NH. And in fact, it's just that the NH is so far broadened out. In the C13 NMR and the carbon 13 NMR spectrum, again, we're sort of like an alcohol, but less so. In other words, for an alcohol, I think for the oxygen bound to carbon, about 50 to 70 ppm. And it's pretty characteristic because by that point, you're down far enough in the carbon, you're away from everything else. For an amine, you're really not that well separated. The carbon that's bound to a nitrogen is in about the 30 to 50 ppm range, which isn't that far from other sorts of carbons that may not have electronegative substituents on them. All right. So that kind of gives the quickie view of the spectroscopy of amines and their properties. And as I said, a lot of what we're going to see, particularly today, is a refrain of some of the chemistry you've seen of amines before, like in the aromatic chapter. So in the synthesis of amines, by way of a quick review, you learned that nitration, that electrophilic aromatic nitration, was a very common reaction and a way to substitute an aromatic group. And the nice thing is it's really, really easy to reduce the nitro group. And your textbook gives 3 different ways, but I can give you 100 different ways to reduce the nitro group down to an amino group. So your textbook taught you that catalytic hydrogenation with hydrogen and palladium on carbon can reduce the nitrogen, or you can use a metal. Metals are reducing agents in general. Metals want to go to metal cations. They want to give up electrons. So iron and hydrochloric acid, or tin and hydrochloric acid. These are 3 conditions from your textbook, and they're all good ways to reduce the nitro group on an aromatic ring down to an amino group. Aliphatic nitros are a little harder to reduce, but they can be reduced by catalytic hydrogenation as well under slightly different conditions. You've learned that lithium aluminum hydride reduces everything and anything. We saw that all the carbonyl groups got reduced down. Esters go to alcohols, carboxylic acids go to alcohols, ketones and aldehydes go to alcohols. And the oddball in the chemistry of lithium aluminum hydride was that because it's hard to kick out the nitrogen in the reduction process, you reduce, you add hydride, you get a tetrahedral intermediate, you end up forming a bond to aluminum, your nitrogen kicks out the oxygen, you add another equivalent of hydride. And so lithium aluminum hydride, LiAlH4, followed by an aqueous workup, reduces most amides down to amines. Lithium aluminum hydride reduces just about everything except carbon-carbon bonds in general. And so nitriles also get blasted down to amines. So if I take, say, benzonitrile and I subject it to the same conditions, I'll just write a ditto mark here, you get phenylethylamine. So immediately you can start to think about ways of making amines where you could start with a carboxylic acid, make an amide, reduce the amide to an amine, or start with an alkyl halide, do an SN2 displacement with sodium or potassium cyanide to get a nitrile, and then reduce the amine to a reduce the nitrile to a primary amine. All right. So one of the other analogies I like to make, because nitrogen and oxygen are very similar in a lot of their structure and bonding. Nitrogen, of course, has 3 valencies. Oxygen has 2 valencies, so there are differences. Nitrogen is less electronegative than oxygen, so compounds with bonds to nitrogen end up being less electrophilic with double bonds to nitrogen. And yet, in many ways, you can see similar reactivity. So in the broadest sense of abstraction, if we have some carbonyl compound, a ketone or aldehyde, and in the broadest sense of abstraction, if we envision adding a hydride nucleophile, and of course you can't go and get hydride any more than you can go ahead and get carbanion. But if we take some hydride source, I'll write this as hydride source, just so you have it for your notes. Of course, you reduce, after some sort of aqueous workup, you reduce, and again, we're talking very broad abstractions here, you reduce your ketone to, or your aldehyde to an alcohol. Now, by a similar token, if we have a carbon-nitrogen double bond of an imine of a ketone or an aldehyde, and again, we have some type of hydride source, H minus in quotes, you reduce your imine to an amine, like so, very much by analogy. Now, this chemistry often gets put together where one can carry out the formation of an imine and the reduction, and that process is called reductive amination, and it's a nice way of making amines. And so again, in sort of very broad view from 30,000 feet abstraction, if we have some sort of carbonyl compound and some amine, some RNH2 amine, and we envision going ahead and again treating with the right hydride under the right conditions, you can both form an imine and reduce the imine, often by way of the iminium ion, all in the same pot. All right, the reagent that's often used to achieve this transformation is sodium cyanoborohydride, NaBH3CN. Now, we've already seen various hydride-reducing agents. You've seen lithium aluminum hydride. You've seen sodium borohydride. You've, I believe, seen lithium tri-tert-butoxy-borohydride. And they all have slightly different properties. Lithium aluminum hydride has that aluminum hydrogen bond that's very polarized. You end up with a very potent hydride source. Boron is less electropositive. It's more electronegative than aluminum, less electropositive. The bond isn't as polarized. It's a milder hydride source. So sodium cyanoborohydride, here's the cyanoborohydride anion, is in many ways like sodium borohydride, but less so. The cyano group is electron withdrawing. It's pulling electron density away. So sodium cyanoborohydride is even less willing to donate a hydride. And that's good because it's not a good enough reducing agent to reduce a ketone, but under the reductive amination conditions, you form as an intermediate, you form an iminium ion. And the iminium ion intermediate is more electrophilic than a ketone. And so sodium cyanoborohydride can add hydride to the iminium ion in the course of the reaction. And so often in one pot, you can mix a ketone and an amine, or a ketone and an ammonia, and sodium cyanoborohydride, sometimes with a little bit of a mild acid like acetic acid, in order to go ahead and form an amine. So if we take benzaldehyde and we treat it with ammonia and sodium cyanoborohydride, NaBH3CN, you get benzylamine. You form the imine, or rather the iminium ion forms transiently, and the cyanoborohydride adds hydride to that and reduces it to the amine. You can do the same thing with a ketone or an aldehyde, so I'll just give you one more example. If you take cyclohexanone and you take, I don't know, let's take neopentylamine as an example, tert-butylamine, not neopentylamine, tert-butylamine as an example, and subject it to the same conditions. So I'll just write ditto over here. Now you can form a secondary amine. Like so. Chemists, as I've emphasized all along, like to be able to build molecules. It's useful to be able to take simple stuff and make it into more complex molecules, yes, including cocaine, which one can synthesize chemically, and morphine. The nitrogen atom is a beautiful linchpin for synthesis because the nitrogen atom is nucleophilic, and so it can act as a nucleophile in an SN2 displacement reaction. So it seems like it would make sense that a useful way to go ahead and build up complexity in a controlled fashion would be to alkylate that nitrogen, but it's not so simple. Usually, the product of the reaction, which is also an amine, or really an ammonium salt in equilibrium with an amine, usually the product of the reaction is even more nucleophilic. So if I take benzylamine and I treat it with methyl iodide, CH3I, even if I use one equivalent, you'd say, well, that should be an easy reaction. I should just get the monomethylated product. And the problem is, as the monomethylated product forms by an SN2 displacement reaction, protons come on, protons go off. As the reaction's proceeding, you have amine present. And so now you have methylamine. So you also end up getting, the dialkylated and trialkylated products. As a mixture. The trialkylated is the benzyl trimethylammonium ion, which is actually used as a germicide in things like eye care products. So the overall result is you get a mixture of products. And so if you say, oh, I want to be smart, I know how to make methylbenzylamine, all I do would be to treat my benzylamine with methyl iodide and then do a basic workup. The problem is you generally, and this isn't always true, but you generally cannot get a monoalkylated product in a controlled fashion. So the big problem is once the SN2 alkylation has occurred, the amino group, well, it's protonated, but protons come on and off under the reaction conditions. The amino group is still nucleophilic and still available to undergo alkylation. In fact, it's even a little more nucleophilic. So imagine for a moment that I wanted to go ahead and do an SN2 reaction. Imagine for a moment that I had hexyl bromide and I wanted to treat it with ammonia. And I've already said on the previous blackboard, I get a mixture of products. The solution that chemists have developed is to take away the nucleophilicity of the amine after it's done the alkylation, to make it so that it's no longer nucleophilic. And the solution to this is called the Gabriel synthesis of primary amines. And it's to use an ammonia surrogate. The ammonia surrogate is phthalimide. PHTHALIMIDE. It's an imide. An imide is like an amide with two carbonyls on the nitrogen. It's the nitrogen analog of an anhydride. The proton, having two carbonyls next to it, is extra acidic. And so a base like sodium hydroxide can pull it off. Your textbook lists a pK of about 10. Other sources list a pK of about 8. And so if you treat this with a base like potassium hydroxide in ethanol, and then Now you pull off the proton, you generate the anion. The anion is nucleophilic, but it's nucleophilic in a controlled fashion. So now if you add your alkyl halide that can participate in an SN2 reaction, if you add your hexyl bromide, now you go ahead, it alkylates, and then what you can do now is in another step treat with strong base or strong acid. So we'll go and treat this with sodium hydroxide. You can also use hydrazine, but we can use sodium hydroxide, water, and heat. And that goes ahead and it makes your amine. And it also makes, as the byproduct, it hydrolyzes the imide. And there are other sorts of syntheses using surrogates, using protecting groups in order to allow the synthesis of secondary amines. There's a Fukuyama amine synthesis, which I won't show you. All right, I think this is a good stopping point. We will pick up with more chemistry of amines next time.